Thank you. Thank you all. How do you build a successful product? Well, the typical scenario goes like this. It starts with identifying your customer needs, then you quickly jump into execution just to ensure you're among the first ones on the market, and then once you're there, you closely engage with those customers to consolidate your market position. And probably you go back to step one again and again. Easy, right? Well, we know that the path to success is never as linear and as simple as it's in the books. And it's neither simple to be part of the engineering team that gets to build that product from scratch. On one hand, we are tasked to build products fast, often having to break some things in order to meet harsh deadlines. On another hand, we are accountable for making precise technical solutions to ensure that our systems will be reliable and scalable in the face of a fast product growth. However, no matter the struggle, we give in all of our best, and we often come to believe that we have found the ultimate technical solution that won't need changing anytime soon. And often our stakeholders agree as well. However, as customer needs evolve, so must our systems. Despite our best initial efforts, we must eventually break the loop to lead to systemic change. And making room for such big changes and slowing down in business, it never gets easy. This is what brings me to this stage today. Over the years, I have been learning a lot from challenges that my engineering teams have faced, so that I became more confident and better prepped to either anticipate future constraints or to lead through systemic changes. I hope my talk does the same for some of you today. My name is Bianca Costache, and I am a senior engineering manager at Adobe Romania. Over the last 11 years, I have been fortunate to be part of engineering teams that built products from scratch. While I always felt excited and proud to be part of something big, I have also continuously felt the struggle between building products fast but slow enough. Fast for our high business demand, but slow enough to ensure our systems will keep up with some of the most demanding customers in the world that either depending on fast real-time capabilities were built or high-throughput data pipes we were deploying all around the world. So by now you can get the gist of it. I'm here today to share a story of one of my engineering teams that designed the product to last until inevitably didn't. I'm not here to champion technologies like Spark or Delta, nor to promote a one-size-fits-all approach. But rather, I'm here to showcase some of the core principles we have drawn from the experience of building data-intensive apps worldwide, and what key capabilities of Spark and Delta Lake have stood out for us in this growth curve journey. My story's main character is Adobe Real-Time Customer Data Platform, which helps companies better understand their users by engaging with them effectively through marketing campaigns at scale. In 2019, my team's mission was to build the streaming data activation pipeline, which would be responsible to quickly and reliably export data to search targeting marketing channels. This diagram showcases the high-level view of our architecture, which still applies to our present. We take in a stream of events, which are then adapted to the various configuration and business requirements for each marketing campaign that a customer might define. What is also worth mentioning is the fact that for one incoming event, we might end up spawning, on average, 100 different events. We have customers for which we even spawn 10K events, depending on the complexity of the orchestration they have to handle for a marketing campaign. In 2019, when we started to build this product, we took in several design principles, also based from our prior experience with building data-intensive apps for marketing at scale. First, we took into consideration that we needed to design for high throughput processing, also being mindful of the fact that we couldn't control neither the input data volume nor its data shape. Then we considered to bring reliability controls to ensure that data is consistently exported given our own systems interruptions or even the performance and health of each such targeting market channel integration. And lastly, because we knew customers will come up and we anticipated the high growth, we considered to balance our development efforts to make it easy to extend our product with new integrations and make it easy to troubleshoot. For our technical solution, we chose Akka Streams. It was a really good fit for our high throughput needs. We also had a local team expertise to rely on. Its back pressure, fault tolerance mechanisms, and non-blocking I/O stood out for us, and it made it really quick for us to roll out production applications. For the data transport layer, we chose Kafka. We needed a highly durable and scalable message system, and we were also fortunate to have an internal team that was operating Kafka at scale for all of us and provided out-of-the-box Kafka client APIs that we could use right away. And lastly, because we just had 4 months to release this, we anticipated we're going to need to iterate fast with deployments. That's why we chose to deploy our apps with Kubernetes. This was also becoming a standard at Adobe, and again, this time we were fortunate to have a platform engineering team that would offer this as a service for us. So the initial design for our first release consisted of a set of interconnected microservices built with Akka Streams, deployed with Kubernetes, and interconnected by internal Kafka topics for separation of concerns and scalability needs. It was a successful one, given that we managed to fine-tune our apps to take in 1 million events per minute. And we launched this, making available 3 destination connectors. But given it was just in the beginning, we actually had on average 1 million events per day, which would spawn up to 100 million events. We considered back then that we would be capable to sustain this for a long run and take in rapid growth. But I know you already know where this is leading to, right? Because reality soon hit us sooner than expected. Our customers started to ask for more and more destinations, so much that our product team decided that the next best thing that we could do was to release 100 different destination connectors. But we had a serious limitation in the face of this requirement, not because of our technical solution, but rather by the time and effort required to cross-coordinate with external partners in order to develop, test, and ultimately deploy a new integration. It took us nearly 2 months to make such a release available. Our response to this challenge and a way to sustain product-led growth in an enterprise world was to release Destinations SDK, which would rather let customers and partners define their own destination connectors, develop, test them with easy controls we provided them, and ultimately make this available for everyone. So we started with 3 connectors, and this year we operate more than 400. This is quite an impressive milestone for us, which also helped us to successfully accomplish this scale. We started with 1 million in one region, and now we had to operate after this release with billions worldwide. Of course, this changed the dynamics of our operations and the way our customers would define complex business workflows on top of our ETL pipeline. We successfully accomplished our design principle to make it easy to extend, but soon after this, all the other core principles started to get challenged by the new traffic scale. First, given our choice of having multiple microservices interconnected by Kafka topics, also by using an internal Kafka client API, made us face this concern. We didn't rely on a thread-safe Kafka client. So this meant that for each app, we would get one consumer thread for Kafka. This meant that eventually, the number of pods of our apps would be bounded by the number of Kafka physical partitions, which were inflexible and not easy to change as we needed. So our only solution in the face of high traffic scale was actually split in two. Either separate our deployments into multiple tiers by adding multiple mirroring topics, or preemptively scale up our deployments, which both of them, of course, added up more costs and operational demands for our team. Another reality of this loosely coupled architecture was the fact that it started to become really hard to ensure data is consistently activated through multiple integration hubs. So whenever we faced a system disruption, in order to ensure data integrity for customers' marketing campaign, we had to replay data. Data loss was not an option in this business case. Of course, this wasn't cheap, and also added more pressure on our team because each release or rollback was treated really carefully in order to meet up our customers' needs. And lastly, given this microservice architecture, tracking data from start to end soon became a puzzle, also because of the complexity of the business flows defined on top of this. Whenever a customer investigation occurred, our team had to look at application telemetry and logs to manually pinpoint where exactly data went wrong. And you can imagine this was not ideal, given the scale we were operating at. So after a continuous operational struggle, we realized that while our design principles were sound, they definitely deserved some amendments. We didn't need it to sustain high throughput processing, but rather with an elastic infrastructure this time. We needed to guarantee reliable data exports, but with automated mechanisms to facilitate exactly one's delivery end-to-end. And lastly, we needed to make it easy to troubleshoot, but not only relying on telemetry and logs, but rather rely on data tools that would help us create an aggregated view of what was happening behind our systems. And we learned that we had no easy way but to migrate to a distributed framework that would provide us the controls out of the box. So we reconsidered our initial technical design of multiple microservices interconnected by Kafka to a model where each Spark streaming job would operate in isolation and would take care completely of an end-to-end business flow from start to end. This meant that we were capable of analyzing and fine-tuning each business ETL flow in isolation, and we also were able to identify one input and output whenever we needed to deep dive into a customer investigation. This time, we also chose not to operate Spark jobs by ourselves with Kubernetes, but rather look at established vendors to do so on our behalf. A vendor like Databricks provided us a practical UI, monitoring dashboards, and even compute resource management APIs we could use at ease to effectively operate this in production. What I would add is that the collaborative notebooks that either Databricks comes with or you can build your own with Jupyter over Spark Vanilla also helped us to onboard new team members on this new mental model and also scale by rapidly testing our code before going to production. This time again, we could also rely on local team expertise to accelerate this change. While there are many key capabilities from both Spark and Databricks you can use, there are several of them that stood out for us, which I'm going to share next. First, it comes with Spark internal execution itself. It relies on a driver executor architecture when you get out-of-the-box distributed controls over data processing, fault tolerance, and compute resource management. All you have to do is actually making sure that you have a sound data partitioning mechanism so that you can actually benefit from the Spark internal graph optimization to ensure that whatever transformation you put in, this gets to be optimized by Spark and ultimately make your apps CPU bound. This is actually what we needed to ensure we're able to cope with scale, but also become cost effective. Another helpful area in this direction was the fact that Spark comes with its own data partitioning mechanism, which you can define at ease. So compared to our Kafka days, prior Kafka days, this time we were able to configure minimal partitions, so we were able to spawn up the data processing of the input Kafka topic in our control and do not depend on an external team to change the number of Kafka physical partitions. And we went even further with this, because what Databricks does, it also comes up with intelligent auto-scaling algorithms you can use. When these are enabled, the Spark driver can actually add or remove executors at runtime, depending on the real-time load, and also based on external monitors that can predict the task load. We explored this in production, and at one point we decided to extend this algorithm by building our own Kafka auto-scaling mechanism. We still use the Databricks APIs, but we were now able to control more these auto-scaling operations based on the service level targets we had to guarantee for each business flow and the nature of each ETL transformation we would operate. The second key benefit of Spark, and also related to the end-to-end consistency, was the Spark streaming checkpointing algorithm. This enables Spark to save both metadata and data while it's processing to a durable storage you can configure. We chose Hadoop file system in our case. This helped us especially given that we had to rely on a Kafka topic as an input, because we suddenly were able to seamlessly save Kafka offsets and operate with releases and rollbacks even, giving the control of operating with precise Kafka offset ranges. And of course, this sped up our development because we were able to iterate fast, but also helped us to become consistent, provide better exactly once guarantees to our customers, so much that the complaints about duplicated data started to drop. Inspired by this mechanism, we actually decided that we could store the input and output of each such business flow to a durable storage. We chose Delta Lake, given its ACID transaction support, schema enforcement, and the optimization layer it comes to operate with a high throughput processing and offering fast operations without impacting actually the runtime processing of your apps. Suddenly, whenever a customer investigation came in, both our engineering teams and this time support teams could actually collaborate on Databricks notebooks by performing SQL-like queries on this data and actually come up with a fast response. We realized that data was no longer a puzzle for us and that we have actually a bigger potential for this. We started to build reporting apps on top of Delta Lake. These apps would crunch historical activated data to provide real-time business metrics to both our customers and stakeholders. Of course, this made our product not be a black box anymore. Everyone was able to see the data and analyze the data. Even the product team could make better and data-driven decisions on top of our product features. And of course, it reduced the number of customer investigations our team had to handle. After exploring this in production, we came to believe that, hey, we have found another technical solution. We won't need to change anytime soon. But of course, this is never the case. Nothing is ever final unless your product is sunset. And we found this reality as we were preparing to roll out the last business flow on this new architecture. This flow, we called it aggregation flow, mainly because it has two main ETL operations it has to perform. First, it takes a stream of events that contain a list of attributes, which then need to be transposed to a message that is keyed of that attribute, and it needs to contain an aggregated set of related events. Both these parameters of how the job can perform this micro batch, either by the size of the events that are attached to an attribute or the time it takes to output such a micro batch, it's something our customers and partners configure. So it's not that easy for us to predict ahead of time and fine-tune this job based on those parameters. Given our prior experience with having too many microservices doing too little, yet requiring a lot of operational demand, we decided to keep it simple and roll out these transformations within a single Spark stateful and streaming job this time. Also, we were confident with the controls we had for auto-scaling and fault tolerance that it would work, even for customers that would spawn up each incoming event to 10K events in this case. But as we rolled out in production, it suddenly blew up with out of memory, no matter how much we tried to fine-tune this job. And the challenge stemmed actually from a vicious loop of issues. First, the transpose operation meant that we had to explode data in memory. For each event, there were more events to be outputted. Secondly, this meant that data had to be repartitioned at runtime. Data repartitioning means that data has to move among executors to be reassigned new data partitions. Data movement comes as well with required memory, and also introduces new I/O operations each executor needs to perform, meaning serialization and deserialization, which also require memory. So after configuring this job and putting it into production, at some point, it would fail by no means with out of memory. So we realized we could not continue, but actually we had to separate the two jobs into individual Spark jobs we could actually fine-tune, each based on the needs of each transformation, and rather rely on a durable storage to reduce the memory pressure it would take for realizing the data repartitioning. And this time, we also chose Delta Lake over the prior Kafka topics we were using to interconnect jobs. We had the experience with activation history, so we have been exercising this for a while in production. We knew that the guarantees it provides actually work for us as well. I take what Hector said previously. You never get to trust the benchmarks until you actually see them in production, and we saw them by using Delta Lake. This also came with the advantage that it is seamlessly integrated within the Spark ecosystem, and it also is the default Databricks storage. And to ensure the service level target, especially the latency guarantees, wouldn't be impacted by us adding an extra hop, we leverage again the resource management API that Databricks comes with, and we developed our own Delta source auto-scaling mechanism to keep the latency in check, but also the cost effectiveness of our app. With time, we have actually became even more confident to make this approach by interconnected several business flows with extra hops with Delta. This meant that we could actually push down predicates into our business flows and make our apps coping with only relevant business data. This is what we all refer to today as medallion architecture. This time, I'm confident that we can take in more and more product growth, but as the lesson learned goes, I'm sure this will only happen up to a point. If there's one key takeaway you can take for my presentation is that the struggle between coping up with fast product needs, but also ensure that your systems are reliable, is here to stay. So at the end of this, I'm just going to draw out some of the core principles I think are valuable for every one of us to consider whenever you need to build such a system. First, I would say it's really important to start with data observability and reporting tools from the get-go. Do not consider them as future enhancements. You might be tempted to say that, well, customer adoption is low at the beginning, so you can keep it up with telemetric and logs. However, you should prefer data tools instead of your team manually doing this, and actually ensure that at some point you are able to delegate repetitive tasks to other external support teams. Aim for distributed frameworks that provide controls for your core design principle. Don't reinvent the wheel like we tried to do. Auto-scaling, resource management, and fault tolerance in a distributed manner were key to us. So always consider whenever you need something, look at frameworks that provide you these capabilities without having your team entering into low-level operations from the beginning. Aim for frameworks that are extensively used within industry and also provide extension points to your needs. While the first MVP goes well in production, and it might seem that that respective framework upholds to your needs, with scale, you always have to be creative and build your own capabilities on top of what that framework provides. And lastly, you have seen from my examples, we have always tried to keep a unified tech stack within the org. Of course, this is not as tempting as we engineers always are excited by new technologies. However, when you operate services worldwide, it's important to look for simple and boring and rather familiar tools that reduce the team cognitive load and also the time it gets to onboard a new team member. And lastly, I think the mantra that I would suggest you to keep close to your heart is this: if you're not migrating, you are stagnating. While undesirable, software re-architectures and migrations are a way of a product's life. But do keep your changes wisely. Do not fall for the shiny technology trap, neither for unnecessary rewrites. Keep your stakeholders informed and aligned, and come prepared with data that showcases progressive results. There's nothing more daunting for business owners than being kept in the dark by engineering teams during lengthy migration projects without visible results. Migrations are not just about the technology and the success of the project, but rather also need to include transparency, alignment, and recognition to make it a real success. Thank you for having me. I am all ears for your questions.